Okay, let's talk about our third and final rigid transformation. It's called translating points or sliding points, which the concept of translations is, relatively simple compared to reflections and rotations. As you've noticed with reflections, the orientation of the object gets flipped, right, or mirrored. The rotation object rotates around a point, so it can kind of get turned. And translations just take points and slides them. Okay, so that's what a translation is going to be about. When we translate points, we can either translate horizontally, meaning side by side, something like this. This point's sliding or translating to the right. It could translate to the left, right? We could also translate vertically, meaning up and down, right? Maybe this point translates down or this point translates up, right? Horizontal, vertical component. Or if we combine them, it's a diagonal translation, okay? So to represent translations and movement, we're going to use vectors. So I'm going to get my little vector tool out here. And let's say this point translated vertically downwards, right? Which we're going to call a negative movement. If it's going to translate vertically, maybe like this, then we're going to call it a positive translation, right? And when we put it on a coordinate plane, that'll make sense, I hope. If a point translates horizontally, then we're just going to translate horizontally, right? To the right is a positive translation. To the left would be a horizontal translation. I'll make this orange here. So we can see that the point is going to translate to the right. So the vector tells us direction, also tells us how far, right? The size of it. How far a point's going to move, okay? Now, diagonally is interesting. There's a lot of math going on diagonally, and we as students aren't super fans of diagonal because of horizontal and vertical logic. We haven't seen a whole lot outside of that. So what we need to understand is that to explain a diagonal movement, we have to be able to see its vertical and its horizontal component to get there, right? And because of the vertical and the horizontal relationship being perpendicular, this actually creates a right triangle, right? This is a 90-degree angle in here. And we all know Pythagorean's theorem, this a squared plus b squared equals c squared. So knowing how to do a horizontal and vertical movement, which are easy to know on a grid, and then we can start figuring out how far points move diagonally, okay? So to help us with this idea again, just to show you, we can translate points. Notice on this image here, Yosemite Sam, I have like 1, 2, 3, 4, 5 key points selected. The top of his hat, which I made blue, the barrel of one of his guns I made orange, his nose is red, his tie is green, and his boot is purple. Those are just key points. I can move points around too if I wanted to. Oops, turn my Smart Ink off real quick. Okay. But I could move points around, but those are just some key points. We could put stuff on his eyebrows, his eyeballs, his ears, whatever we wanted to stick out, right? When we translate, every single point gets transformed the same way. Notice those key points move along with every other point that makes the image. So we can move horizontally. We can move vertically, up and down, right? But when we combine it is where we're going to start getting diagonal thought. Remember, if one point, when we translate one point, every single point gets translated the same. So notice this point moved down because of vertical translation. I made it a -1, meaning down 1 on the vertical. And to the right 6. Notice my horizontal movement is a +6. Okay? And not only that point, but every single key point, including the ones I'm not even showing here, are translating by the exact same vector, right? They have the same down 1 over 6. Okay, movements. So as I move these around, no matter what we do, every single point is going to get behaved by that vector. Okay? So I'm going to throw a couple thoughts out at you here. This page here says how many points are a distance of 3 units from the origin on a grid. And the way that we can think about distance is a translating distance, right? So I'm going to put the origin right there at A. I'm going to make my points hopefully stand out a little bit, make them a little bigger. So how many other points are, well, how many points are 3 units from the origin? So here's where most of us, I believe, are at. If I asked you to plot all the points that you think are a distance of 3 from the origin, I hope that you would at least see that we can go to the right 1, 2, 3, right? We can move horizontally, translate from the origin 3 units to the right. We could translate from the origin 3 units to the left, right? These are just horizontal movements. On a grid, we can count horizontal and vertically accurately and confidently. It's that diagonal movement that becomes a little bit different. Okay? How about if we move down? Notice down here I can go down 1, 2, 3. So here's a third point that's 3 units from the origin, and just like we can go down, we can actually translate up 3, right? So those 4 points, are they the only 4 that are the same distance? Okay, segment length, when we talk distance, we don't necessarily have to have a vector. Vectors show us translation, like going from the origin out to these points, so we would have an arrow showing direction. But we can also just show length, right? Segment length. So maybe I'll make these red. So notice that segment has a length of 3, that segment has a length of 3, length of 3, length of 3. Those must be the only ones. Unless we kind of start opening our brain up to translating or moving not just horizontal and vertical, but combined. How many more points are there? And the answer is there's an infinite amount of points that can move a distance of 3 units to from the origin. And I hope you're understanding circles. I'm going to make this red. If I make A the center of my circle and I go out to one of these points, notice all those distances are the same, hence they're radii of the same circle, right? And we kind of see that square construction that we had earlier. But more importantly, if I put any point on the circle and connect that point to the center, isn't this radius going to be the same length as, say, this radius or this radius? Any of these? So notice how many points are a distance of 3 units from the origin? There's an infinite amount of points. And depending on how their relationship, this diagonal, is concerned, we could figure out where that is. And using this concept will actually help us come up with the equation of a circle on a grid. That's for a later date, but we could definitely use that concept. And here's how we do that. Every single point being diagonal is going to have some vertical, meaning moving up, and some horizontal, meaning moving over, component to it that allows us to create this diagonal distance here. Okay, so let's try this here. I'm going to just, you can watch me on here. You don't have to do this as you watch, but I'm going to grab my parallel line tool. Okay, this toolbox here, this fourth one from the left, is called our construction toolbox. All these lines that we can use, like perpendicular line, perpendicular bisector, we've constructed those. We will construct parallel lines and angle bisectors as well. We could construct these, but we're not going to just construct these different kind of lines here. So anyways, parallel line tool. Let's show the vertical movement from A to F. So what I'm going to do is I'm going to click on point F. And then I got to click on a line I want to be parallel to, which will be like the axis. So I'm going to go to this axis and click on it. And notice now I have a line that's parallel to the y-axis. And no matter where F is, notice that line's always going to stay parallel. Okay? Now let's go ahead and show the horizontal movement to go from A to F. So I'm going to grab my parallel line tool again. I want my horizontal line to go through A, and I'm going to be parallel to the x-axis. You can't really see that line. What if I made these lines blue? So now that line's blue, and I'll make this line here blue. Okay, so now when I slide F around, okay, we just have these lines, this vertical line and this horizontal line. Notice from A, this horizontal line is not going to move, and that's okay. What I want to show really is this distance here. So I'm going to grab this intersection point. And now if you notice a triangle, we have 3 vertices. We actually have if this is a right triangle because of the horizontal and vertical lines, right? This is always going to be a right triangle no matter where our segment is. It's always going to be a right angle right here, and I can actually measure that. So I can show that this is always perpendicular, hence the vertical and horizontal. And now when we look at triangles, maybe I'll make the segments green so these will stand out. Here's a side of our triangle. Here's the side of our triangle. This is just the horizontal component, vertical component, and the actual translation. So I hope you can see a right triangle in there. So any point on a circle, or any point that's translated 3 units to the right, are going to have this horizontal and vertical component. And because of Pythagorean's theorem, we could always find missing lengths of a right triangle, which we will do later. Okay, so how far does a point move? I want you guys to start thinking outside of horizontal and vertical movement. Start thinking diagonal, which the collection are all these points right here. Okay. Okay, so now that we talked about how to translate diagonally, let's talk about how to translate with a vector. There's two ways that we're going to see vector notation. And these are, so just so that you know, vectors they look like little rays. It's just an arrow, kind of like this, to show direction and distance. But rays to show us how points are moving. Two ways to see notation. You'll see a horizontal notation like this. It uses these pointy brackets, unlike ordered pairs, where if I told you, like, for example, here's the y-axis, here's the x-axis, and to plot the point 2, 2. We use ordered pair, these parentheses, which we would know from the origin we would translate 2 to the right and 2 up, and that point would be right here, right? It's kind of like that, except we use notation with the sharp brackets like this and say 2, 2, which say no matter what, give a point, say this point here, if we're going to translate with this vector, then we would just move the point 2 units to the right and 2 units up. Same deal with a vertical representation. Vertical representation uses our ordered pairs, except we would say something like this, 2, 2. This is going to be the horizontal movement, the first one. The second one tells us how far vertically to move. So let's do another vector. Let's say we were going to translate a point by -1, -2. This is my horizontal movement. So I know that I'm going to take this point, move it 1 unit to the left. This is my vertical movement, so I know that point's going to move down 2. So 1 to the left, down 2. That vector tells us we're going to translate to this point. Okay? So that's how we see vector notation. You're either going to see the horizontal with the pointy parentheses, kind of like an ordered pair, just pointy, and then we have the vertical notation as well. Okay? So let's go back to this question here. Let's translate this triangle by the vector. It tells us horizontal component, so we're going to go to the left 2 and up 5. So if we have a blank plane here, it's hard to see, and that's why with translations especially, we want to be able to see a grid so we can see horizontal and we can see vertical. So here's how we translate using GeoGebra. We have to set up the vector first. So in my line toolbox here, at the bottom we have vector between 2 points. So what we need to do is place a vector anywhere we want on the screen. So just pick a point somewhere, and we don't even need the grid. Just pick a point somewhere, and we're going to go, maybe right here, we're going to go 2 units to the left, and then we're going to go up 5, 1, 2, 3, 4, 5, and place a point there. So this vector takes a point, and it moves it 2 units to the left, up 5. So now we can translate this triangle, wherever it happens to be, 2 units to the left and up 5, just by using this vector. So in our transformation toolbox, I'm going to grab my translate object by vector tool. So what we have to do is select the object we want to translate, and then we just select the vector that will translate it. So notice now my triangles have translated, and if I wanted to, I can show, like B, for instance, goes to B prime because it moved 2 units to the left and up 2, 3, 4, 5, right? A moved 2 units to the left and up 1, 2, 3, 4, 5. And C moved the same, 2 units to the left. Oops. 2 units to the left and up 5. If I can get that to work. Weird. Why is that tool not working? It's not liking me clicking on C. But anyways, you can see, I hope. 2 units. This is backwards. Weird. So let me do that vector. Anyways, that's how we use vector notation to help us know how to translate points. It tells us directions in which way the object is going to translate.